Okay. Hi, good evening, everybody. Thank you for joining us this evening. My name is Dorothy. So I am a HR coordinator of the talent acquisition team of Rakuten Asia. So to kickstart this session in the evening, so I would like to share a little bit more about Rakuten Asia. So I would like to share that Rakuten was founded in 1997 with only 6 employees and one business, which is our Rakuten Ichiba, our e-commerce website, and also one server and 13 merchants in Tokyo. So right now, we have 70 over businesses around the globe in 30 countries and still the number one largest e-commerce company in Japan. So we do have an ecosystem. Apart from Rakuten Ichiba, which is our e-commerce website, we are currently now in terms of businesses, we do have commerce, communications and energy, fintech, investment and incubation, and media and sports. So I would like to bring us closer to where we are today. So we call ourselves Crimson House Singapore, which is the place where we host our sister companies. So some of them we have here. Allow me to share, we are Rakuten Asia. We are part of the global expansion of Rakuten Inc. So we are situated here at where you are today. And these are the sister companies that we have. So I'm not going to share all of them, but critically, I would like to share this today, which is Rakuten Institute of Technology, because our speakers today are actually the research scientists of one of our sister companies over here. So this particular sister company that we have actually specializes in it's like our think tank on research and development. So over here, I would like to quickly also share mission and vision statement. So at Rakuten, we contribute to society by creating value through innovation and entrepreneurship. We empower other people to realize their dreams. We embrace new thinking and we change the world through innovation. Our current ambition will be becoming the global innovation company. So at Rakuten, we drive disruptive innovation, we draw knowledge, creativity, and passion from around the world to achieve ambitious goals, and we help build communities in which people can pursue their dreams and live in happiness. Next, I would like to take this opportunity to share some of the partnerships, the global partnerships that we have. I think some that we are pretty familiar with was previously our sports partnership with FC Barcelona. Recently, we had continued our partnership with Stephen Curry. So that is where we actually worked together on the Stephen Curry Underrated Tour, and also Shakira, and in between with our Tokyo sports teams as well. Next, I would like to share the closer to where we are today, our office concept and some of the common policies. So right now, where we are situated at Capital Green, Crimson House Singapore, where we name ourselves. In terms of diversity, we do have about 70 over nationalities in our workforce as well. And the current workplace that we share is an open space concept. All of us can come together and do an open discussion as and when we want. And of course, I have to say, where we are today is my favorite place in the office as well, because of the view and the chillax concept that wherever your brain needs to take a break, you can just come here and take a break as well. So these are some of the offices that we have. We do occupy right now 4 different levels in the Capital Green building, 7, 8, 29, where event space and meeting rooms are, and also other offices that are available at level 32. We do have a mini gym over here, and this space where we are at today is where we host most of our monthly happy hour. I would like to share something that we are also proud of. Our office is actually previously featured in the Smart Local as well. Almost coming to an end, I would also like to share that Rakuten Asia have been also awarded with a Great Place to Work certificate for at least 2 years. Yep. So as employees over here, apart from work, we do have interest groups as well. So we do have people who have interest in soccer, in yoga, and they all come together and have a session after work as well. Here, I would also like to share, apart from this session today, we are also trying to host tech talks and events on a monthly basis as well. So we do see a show of hands just now for returning listeners as well. So we are looking forward to hosting such events again on a monthly basis, and we will be able to see all of you again. Yep. So last but not least, I would like to share at Rakuten, we are always on the lookout for new talents. So this is the QR code on the right, where you will be able to access to our LinkedIn page to check out the current openings that we have. And last but not least, I would like to also urge all of us to follow us on our social media account. So what can you expect out from following us on Instagram is you will be able to know when is the upcoming next tech talk that we have, and also the culture that we have at Rakuten Asia. So that is actually all that I have for the introduction. I do see that there are still some of us trying to scan the QR code, so I'll leave the screen on for a while. All right. Thank you so much for listening. Are you still on it? So, all right. Thank you so much. So without further ado, let me just welcome my colleague here, Max. Then he will be able to share a little bit more about machine learning today. Thank you.
So we can be turned off. Just a few moments. All right. Well, thanks for great introduction, Dorothy. Let's jump into a little bit of technical discussion. And today we're going to talk about evolution of language modeling from n-grams to transformers. Oh, I'd like to start my talk with people and communication. So we are social creatures. We communicate, we work together. We achieve our goals by using this fascinating tool, language. But now I want you to imagine the world where computers can understand our language too, and can be very good helpers in our day-to-day life. But they can help coding, as code. I assume a lot of you from backgrounds of data science and as such, raise your hand if you are. Great, quite a few. So we also seen a lot of examples of language models helping us to write the content and so on and so forth with ChatGPT. And it's just really a nice endeavor to enable computers to understand human languages, to normalize the interface with the computer so that we can communicate easily. And all the recent advancements in natural language understanding have been driven by the development of large language models. Oh, what is large language model and what is a foundational model, another term for that, is not really clearly defined, but well, we can assume that it's a big neural network with over millions or billions of parameters to train to do a very specific task. And in this talk, I'm not going to go into details of how these models work. Rather, I want to offer you a basic framework of thinking about language models that stems from the way past, from 1950s and so on, and develops in more elaborate models that we use today, which is transformers. And all the large language models nowadays are using the same architecture, starting from around 2018. They all use transformers, and they all listed here on the slides, just such as GPT, BERT, and so on and so forth. Well, what does this language models really do, right? And if I were to summarize the whole talk in a very short sentence, what they do is to play the game. And the game is to fill up the blank. Here we have a couple of sentences, and we're asking either the person or the model to fill up what word is appropriate in this context, right? Now, you may stop me and say, well, it might not look like a worthwhile endeavor, right? It's not a path to general artificial intelligence or something like that. Oh, but it turns out that this kind of sort of pre-training or training the models to predict the next word or to predict the word within the context is quite a good approximator and very useful one to understanding how the language works and to understanding different information about our environment. For example, let's take the first sentence here, Stella A. So in this case, we need to assume that we're talking about something eatable, right? If we go to the second sentence, we introduce in more context, so we're probably going to talk about food in Singapore. So we better use something that is related to Singapore. It requires a lot of bits and pieces of understanding. And Dorothy also mentioned that we have quite a few businesses here, right? And you can fill up the blank, right, of what business can offer and reveal the recommendation of Cherry Blossom Beauty, right? So it requires a kind of understanding of what Rakuten does and what business it has to fill the blank correctly. If you were to fill the blanks, we can have something like this: spaghetti carbonara, lure me, and travel, Rakuten travel. So let me kind of prove to you that it's a worthwhile endeavor by showing a couple of examples, right, of how language models can be used to make your life easier. Here I have a GitHub Copilot that, well, some of you might use to develop software. What GitHub Copilot does is suggest you code. You can write something in a comment, and you can ask it to complete the code. And here, what I'm asking is determine whether the sentiment of the text is positive and use a web interface. So in this case, Google Copilot is going to write this code for me. I don't need to do anything. So you already kind of see how destructive this can be, how it can accelerate the development process, right? The software development process. Another example is Microsoft Bing chat, or I would call it a chat, that uses ChatGPT, that uses GPT-4 to reply your request. And here I used standard examples to write a poem that rhymes with 8-year-old Jake. He loves dogs and facts about the ocean. And let's see what it writes. Now, if you look at it, it's very impressive. It writes a poem. It follows your instructions to the letter. Like it rhymes it with Jake at some point, and also shows love for dogs and ocean. Oh, you can see again how this technology can disrupt things like copywriting, right, and so on and so forth. We've seen a lot of examples of that even before large language models were introduced, but not at the scale we have it now. Translation, right, can be useful when you travel, right? Or maybe you used Grammarly or something like that to correct your grammar. Oh. Well, so with this in mind, well, again, I want to introduce the basic framework how to think about these models without going much into details. And we can do that through the lens of the history. Right, and here's allusion if you watched Back to the Future or Rick and Morty. This is a copyright-friendly version of this. Now, let's go into details on what the language model is, right? And let's start by asking the question, which sentence is more likely than the other, right? And I want to say that this is a worthwhile question to explore. Why? Because we can use it for many, many applications. We can test the common sense, right? I had a great dinner in the evening, more likely than to have a great dinner in the morning, right? So just by having this course, we can kind of induce the common sense into machine. And probably the sentence that contains the mistakes is less likely than the sentence that doesn't contain a mistake. So we can use it for grammar correction. Or we can use it across different applications, such as machine translation, to understand among all the plausible responses, which response is more fluent. So actually looking at this, right, asking this question and formalizing it in a more strict way, such as a probability distribution and comparing the probability distribution of sentences, we can get already some gain and use it in our applications. So, and here I'm going to be using this notation. Not a lot of math in this talk. I'm not going to go in details, but just to keep a little bit us framed, I'm going to be using the probability notation, and I'm going to be using a little bit of this beginning of sentence tags and end of sentence tag. We'll see why it might be important later. But you won't need to understand in details what the probability distribution is. Well, let's start by creating a story machine that would write a story for us. And let's start with a very simple one, right? Let's respected data scientists, let's take a corpus of text, right? A collection of texts, look at all the sentences we have in this text, write them on the pieces of paper, right? And put the sentences in the bag. So in this way, we already have a kind of functions that tells us, right, which sentence is more likely. Is some of the sentences going to occur multiple times on the slide, right? And that's indicator of the score, which sentence is more likely, right? And now we're going to use the following generation process to generate our sentences. Oh, we have this bag named language model. Oh, what we're going to do? We're going to put our hand in the bag, take a piece of paper, put it in front of us, write the sentence down, right? Put the piece of paper back. Right, and if you've heard of something called bag of words, right, well, this is a bag of sentences, and we can continue doing so, generating sentences more and more, like to complete the story. Now, of course, there is a problem with this model, right? It doesn't consider the context, it doesn't look at what the previous sentence is, right? And it's something we want to fix in the future. But let's now fix on the other part. Right? Language is infinitely large. There are so many sentences that we can generate, right? At any point of time, we can just create a new word, or just take an existing sentence and add a few words to it. Right? We can't really think that we can write all the possible sentences human beings are going to speak, right? Well, we need some kind of mechanism to generate new sentences out of pieces. Well, it may be worthwhile to consider a simpler model than the bag of sentences. It's a bag of words. So what we do here, we take the pieces of sentences from a bag, we chop them into words and put the words back into the bag. Now, our generation process is a little bit different now. We'll start with the beginning of sentence tag. We start drawing the pieces of paper from the bag till we reach the end of the sentence tag. And that's where I needed the end of the sentence tag. And you also need to put the pieces of paper back in the bag, but for the sake of this discussion, we're just gonna draw pieces of paper from the bag. And you can see that you can kind of generate very plausible sentences that you've never seen in a corpus before, right? So dog likes boy. And I have to say, we're very lucky to get this sentence because most of the time you'll get nonsensical things like this. Right, and the problem with it is that we went through the extremes. We went from the sentences, chopped them into words, right? And it's not very nice to do that because we are losing a lot of the context. Our previous model, we're generating the really nice sentences, really nice, well-formed sentences, and here we can't have this behavior. Well, maybe it's worth to try a little bit more context, right? And we start writing 2 words at the time on the pieces of paper. And now, first of all, we're going to waste a lot of paper, but it's okay. So we need the magic scissors because for what we want to do here, we want to slide for every 2 words, right? We want to sentence "this boy likes the dog" actually to translate to the pieces of paper like the boy likes the dog end of the sentence, right? So we need to have a magic scissors so that we can duplicate the sentences. But we do the same thing, we put them into bag. Now, our generative story now is going to be a little bit different, right? We're still going to start with the beginning of the sentence, right? With the beginning of the sentence tag. And we're going to draw pieces of paper from the bag that would overlap with our drawn before tags, right? And we're gonna continue writing the sentence word by word in this case. Now, this task already seems kind of familiar because, well, the same as in large language model, we're asking ourselves the question, well, here's the context. What is the next word for this context? Right? That's a very huge thing. And there is nothing really that happens otherwise there, right? It's just the way that we can distinguish the context and in large language models and in n-grams. So, but anyway, let's get back to this, right? Sometimes we can draw the pieces that don't overlap, right? In this case, what we do, we put these pieces of paper bag, and we continue drawing the pieces until we kind of form a well-formed sentence. Now, again, I've been a little bit lucky here, right? I'm drawing a nice sentence here, but later I'll show you an example and let you judge of how good the n-gram models are. And to be honest, they're very impressive for what they are. Now, seamlessly, I kind of introduced you what all the n-gram language models are, right? We used one word, that's 1-gram language model, unigram or bag of words, if you wish. We have 2-gram language models that uses 2 words at a time to generate the sentence. We have a tri-gram language models, and we can increase the number of words that we use, that we draw from a bag, to generate more and more sentences that would see more and more context in this case. Now, we learned quite a bit of information, and let me stop and put a little bit of math into it so that we know what we're talking. We actually learned how to score the sentence by splitting it into pieces. Well, it might not be that obvious, but when we want to draw a sentence like boy like girl, it's a combination of our simple process of drawing each word independently from each other. The next one we introduced, so we can look at the context when we're drawing the words. And that's important, that becomes important because then our task becomes, so here's the context, what's the next word appropriate for this context? Now, I'm introducing here conditional probabilities. I haven't really explicitly talked about it. I made a trick there. I was rejecting the samples that wouldn't give me the conditional probability. But, well, it's not that important. Our process from the bag is very slow and inefficient, but if you were to code it, it's very fast. You can execute it very fast on the machine. And we also learned the kind of a trick, how to estimate the parameters of the model. Again, it might not be obvious, but we have the conditional probability parameters, so we have the singular parameters here. And they're all proportional to the joint distribution, actually, they're proportional to basically the counts of how many this word occurred, let's say, in my bag, right? And that's exactly the thing that happens with pretty much every language model, as we learn to explain the corpus of the text, right, the collection of the text through these basic parameters. And we use exactly the same technique for training large language models or any language models, except we're still using maximum likelihood estimate to penalize the model when it outputs the wrong word, and so on and so forth. Well, here's an example, right? So how powerful n-grams are, and I'll give you a few seconds to read it and judge it for yourself. This is an n-gram language model. It's trained on Shakespeare. You can see all the problems that we've seen before, probably, and but the more n-grams we use, it seems like it becomes better and better. It still loses a kind of context, right? Context dependence. It doesn't really have this good sense. What's interesting is, like, our model is kind of discrete, right? So we just counting the words here, right? And if you start counting the n-grams large enough, we're gonna run into a problem. Let's say we have this training data, we have this testing data. We're never gonna be able to generalize from this training data to the sentence, John loves Mary, right? And in this world, if you were to replace John with a machine, right, the John is going to be trouble, and the Mary is going to be, oh, do you love me? This nature of discreteness is quite a problematic, right? But there is an elegant solution to overcome this discrete nature of n-gram models. And well, the gist of it, we want to represent words not by the count of how many this word occurs in the context, but by the count of the context, right? And in around 1954 was great minds were saying pretty much the same things about, well, how can we represent the word? And if A and B have almost identical environments, we say that they are synonymous, right? So, and you can see why it is. I'll show as well example why is it true, or you shall know the word by the company it keeps. What it really means is, well, let me tell you. Let me give you a simple example, right? Similar context, it's roughly equals similar meaning. What it means is that suppose I ask you what a slangus is, right? So, but instead of telling you exact definition of what it is, right, I'll start giving you sentences where I use this word, right? And well, right, at the end of the day, I'm going to give you the definition, right? So it's a Hungarian food specialty, deep fried dough. But look at the sentences, and you kind of could have guessed that we're talking about food. It's made of flour. Well, it's probably some kind of bread, right? So, and you can draw the conclusions from how similar it is with what you know, right? What would you use in this context? Oh, counting word meaning is easy if you have a big corpus. Here I have a kind of cherry-picked corpus to demonstrate the issue, like that, demonstrate how we can use the context to approximate the meaning of the word. And we have words like for and adversary and data and information. And if we count enough times, we'll start seeing clusters like this, right? That would represent that these words actually tend to have a similar meaning because they occur in similar context. And this observation was taken to advancement. So the problem with counting the context of each word in a large enough corpus is that your table of context become very big. It's not very useful to manage so many parameters. What you actually want is a small vector that you can operate, right? And you want to have some properties of this vector so that they're going to be close to each other when the words are similar. They're going to be far away from each other when the words are not similar. And word2vec demonstrates two concepts, right? The first will be able to compress this big table into small parametric vector for the word. And it's able to do that using the self-supervision. So what word2vec did is, we have a sentence and we have a right word for the context. Right? And what we're going to ask the model to do is to distinguish between right and wrong context. If the model says, well, it should be a computer, we have to penalize it. If it's a for, we have to reward it. Now, one of the essential property I already mentioned is that similar vectors, like if you're projected to 2D space or any sort of space, are going to be similar to each other. And here to measure the similarity, I use cosine distance, like data information going to be close to each other. Frog or any random word is going to be far away from this thing. And just to represent this space of word2vec vectors projected on 2D, you can see that there's some cluster of politics, violence there, and so on. Just an example. But, well, we were talking about language models, right? And it's a little bit different, what we just seen. Well, kind of the task is similar, right? We are asking this word2vec to predict the correct context and distinguish it from a wrong context, correct word in a context and distinguish it from a wrong word in a context, right? We're still asking the model to fill up the gap, right? But the issue here is that this model is not yet a generating machine. It can't be used to generate sentences that we used to do with n-gram models. It solves quite a bit of things because, well, probably the boy is going to be close to the girl or word in this space, in semantic space, and we achieve some kind of generalizability here. Like is going to be close to love, and so on. So we kind of going to save John. The problem is how to put this together to ask the model how to generate the next word in a given context. I'm going to give you the just general framework of more or less what all the neural networks do. We feed our word vectors into some neural network, right? We ask this neural network to produce another vector for the new word. We take this vector and map it into the space of our vocabulary. And so basically ask model, oh, tell me what words is really the next in this case. And we compare it using the supervision method with the target word in this context, which is boy. And if the model does a wrong choice, right, we penalize this model. If the model is correct, we reward it. And in totality, if we iterate through the whole corpus, right, of our sentences or our text, what we're actually estimating is a conditional probability that we've seen before in n-gram models. And it's really great because now we can use all the techniques that we used before to draw sentences. What we actually came back to is a bag. So it's arguably a very complicated bag now. It has tons of parameters. But still, we can ask all sorts of questions like what is the most probable word in the given context, or we can sample the words to give us interesting text. Well, let's talk a little bit about the timeline of these things. I talked about a little bit about n-grams, and that's development of 1950s or even earlier. Dimensions of n-gram models kind of goes to 1913, but of course it was not widely spread, and that the n-grams came about and received a widespread when Claude Shannon published his mathematical theory of communication. Then I talked a little bit about word2vec, and that's 2013. So the n-grams were pretty much quite dominant for a very long time. But the interesting fact, maybe a little bit unexpected, that the neural net language models were introduced in around 2000s, or maybe even earlier. So now all these concepts of training the word embeddings and use an end-to-end system that goes from that's trained in a self-supervised way goes to a very early days. And what we have now, and what we have now de facto, is state-of-the-art model, state-of-the-art architecture for all the things that we do in NLP, and maybe even beyond NLP, such as vision and so on. Well, let me focus on this stretch from 2000 to 2017 and show you a couple of models, right? That's practical models that have been used to generate the next word for a sentence given a context. And here I use convolutional neural networks to do that. Basically, I'm looking at the 3 previous words. Every convolutional layer looks at the 3 previous words, generates the next word given the previous context of 3 words, so depending on convolution. Now, this model is quite nice. It looks at a lot of context. It's still kind of problematic in this sense. It has the same problem as n-grams. It's limited. It can look at what history it can look at. Of course, if you can stack more convolutions we'll be able to capture more distant context, but overall there is a problem. So another architectures that were quite popular for language modeling were recurrent neural networks. An idea is that we basically loop our network. We feed the same our words for at the time t, right, to the same network to generate our words, the next probable word, and potentially it can capture a very long dependencies, infinite context. Theoretically, it can capture infinite context in the sense. And what we've come here is very elaborate and model that is designed to overcome a lot of problems, which is transformers. And well, two very popular models, right, that been used for in quite a bit of applications across companies and across research, BERT and GPT. Let me talk a little bit about both of them. Just a few glances at it. Well, BERT is conceptually more similar to word-to-vec than to a language model, really. Because what we do in BERT, we mask some of the words, and we ask this model to predict a word in a context, and we do exactly the same thing. We pass our vectors to the transformer networks. We ask it to generate a vector for the masked tokens, and we project it to the space of words and compare it to the word that is good in this context. If it's bad, if the model generates a bad word, then we penalize the model. If it generates a good word, we reward the model. And it's kind of good to use this model to come up with the contextual representations of the words. Is now we can distinguish different meanings, different connotations of the words. Like and love going to be a little bit different depending on the task you're solving. BERT also introduced a notion of kind of embedding for the whole sentence or a whole chunk of this class, the first artificial token, this class token, that can be used for a variety of tasks, such as sentiment classification or just any classification task, or even ranking in the search. Well, OpenAI GPT is more like a traditional language model. It really focuses on, well, given this context, let me generate a new word, right? And can complete the sentence word by word. Once we generate it, we can repeat this, our n-gram process to generate more and more words, and hopefully to get some useful information out of it. Oh, here I kind of go to the end of my talk for this. So what happened is we look at the task of language modeling, right? And we figured that it's basically predicting next probable token, right? But in the next talk, what we want to explore is now we have this learnable machine that can generate the next word, how to make it more useful for us to be able to communicate, to be able to use APIs and so on and so forth. Oh, thank you very much.
Oh, God, so sorry. Yeah. Hi, just wondering if everyone is back. Sorry to stop your conversation right now. All right, thank you so much, everyone, for waiting. So, just up next, we have Johanas here. So he'll be continuing the part 2 over here. Thank you, everybody, for your attention. Johanas, please.
Check. Can you hear me? Okay. Yeah. Thanks for the introduction. So, okay. So let's from next session, we already have a large language model, and in this session, we will see how we can use it for NLP. I'm Johanas. I'm research scientist from Rakuten Institute of Technology. So let me put a disclaimer first. This talk is not about explaining how good ChatGPT is, like an influencer or something. So, and feel free that this talk is also not about theoretical and mathematical foundations of LLM. So, yes, but what this talk is about, we see recently there's a lot of jargon on the social media. LLM, Bloom, Llama, prompt engineering, whoa, whatever. This talk is about how to map how far everything has progressed and look beyond the hypes and trends. So let's first see the paradigm shift in NLP. So if you remember, around 2015, we trained an SPM model, CRF, decision tree. We do feature engineering. If this word appears, if this word not appears, if the price of the house is more than this much, that much, that's feature engineering. And it's non-neural model mainly used. And then somewhere around 2013 and 2018, we train CNN, RNN, LSTM, GRU. We decide which cell to use. We rely on neural networks, and we don't need to manually define the features. We modify the network structure instead. How many layers we want to use? Should we stack more layers? Should we change the layer size? That kind of thing. That's architecture engineering. And then next, we see objective engineering. We have a BERT, let's say, a pre-trained language model. It's used as an initialization of full model. We take the last layer, we change it with a classification layer, for example, for sentiment analysis. And then we fine-tune the BERT, everything. We do less work on architecture design because it's BERT, and we just remove the last layer, change it with classification layer. But we engineer objective functions like the last layer, the loss function. And recently, there is a prompt engineering. Prompt engineering is an NLP task that are modeled, NLP paradigm that are modeled entirely by relying on large language model. It can be done because language model now is good enough, large enough. So the task of feature extraction, if this word appears, if this word not appears, and the prediction of the data are given to the language model. What we do, we engineer prompt instead. The example is when we do prompting GPT-3, for example. So the task definition for each NLP task is also changing. Before, for each task, it has different interface. Interface means like how the model receives the input and generates the output. Architecture, the shape of the model, and the expertise. Let's see that there are 7 mainstream paradigms in NLP. Here we have classification. So it receives text and the output is labeled. So it's sentiment analysis, something like that. And there is a matching. We got a text A and text B, and output is labeled, something like a textual similarity. And there is also a sequence labeling. We receive like sequence of word A, B, C, and the output is like the label for each word. It's something like a name entity recognition. There is a machine reading comprehension. So we give a paragraph as a context and we put a question. It will extract some sentence or word that answer the question. There is also a sequence to sequence. This is, for example, like a machine translation. We put the source sentence and it encodes and decodes the target sentence. And there is a sequence to action sequence. Like we put a sentence, like a command, for example, and the output is like a action sequence, like a robot. Should it go forward? Should it turn right? Should it turn left? Something like that. And finally, there is a language modeling. This is, we give word A, and then a mask, and then word C, and then it will try to predict the missing word B. So for all tasks, if we change all of this definition to language modeling, it will have the same interface and it will have the same architecture because we are just using the same language model. So there is this complicated figure from Sun and colleague. I really like this. There is this is the 7 main tasks of NLP. We have classification, sentence matching, and so on. And let's say in 2012, we give the same weight, same width between all lanes. And then moving on to 2021, we see that the red one here, language modeling, actually becomes bigger. Maybe you cannot see, it's 286. So from 100 to 286, that means like 2.8 times more tasks are being solved by language modeling paradigm. And where does it get the wake from? We see that around 2019, the sequence to sequence, some part are changing into red here. And also machine reading comprehension, something like question answering given a paragraph. Some parts are becoming language modeling tasks. So again, we just need to formulate the prompt. But what is prompting? Like I keep saying prompt. Language modeling language model task is to guess a missing word, like we discussed in the previous session with Max. So let's say the sentence is, I go to, and then there's a mask to buy groceries. It can be shop, can be market, it can be anything. But then let's say we move the mask to the back and change the sentence like, I like this, I love this movie. Overall, it was a mask movie. Language model can predict this as any word. Let's say we put a list of words that means positive and list of words that means negative. If the mask is predicted as terrible, disgusting, or bad, we can say that the sentiment is negative. And if the mask is cool, marvelous, fantastic, we can predict that it's positive. So depending how we prompt the model, we can actually make the model to do a task, an NLP task that we need. We can ask, like JDK is developed by Oracle. This is like answering question. This is a super long text, TLDR. This is a summarization. And birds can fly, like common sense reasoning. And if it can complete a word, can it also complete a sentence? Yes, it can. Like recently, decoder-based large-scale language model. Well, I write it like this, but GPT actually, one of them, like it's able to generate multiple words, which is sentence, and it's multilingual. So let's say like the sentence, I give the prompt as the primary color is, and then the model will complete it with red, blue, and yellow. I put the sentence at the prompt, the 6 naturally occurring noble gases are, and it will answer like this. Let's reshape the prompt so it generates translation. Hello world in Spanish is Hola Mundo, something like this. And this is the translation. And I can change the shape also into something like this. Let's say that the Spanish is on the second line, and it can still answer. So changing the shape will affect the result sometimes. But wait, why it works? It looks magical. If language model is just trained to complete a missing word or sentence, how can it do such an NLP task? Because in the training dataset, there are multiple similar sentence patterns. We found that there are at least 5 shapes of prompt to do translation. We replace the L1 with the source language, we replace the L2 with the target language, and we put the source sentence here. And we can also make it like, given the following source text, and then we put the sentence, a good Spanish translation is, and the model will give the translation. Depending on the type of prompt you use, the result will be different. So who keeps track of such pattern? And how do we know which prompt works best? There is a public pool of prompts. There is an interface called prompt source. They collect not every kind of prompt in NLP task. Let's say there is a translation, sentiment analysis, common sense question answering, summarization, movie review, and so on. And this kind of crowdsource gathered by contributor prompt are gathered into a dataset that we call P3, a public pool of prompts. And we discussed before about having GPT as a foundational LLM. It can be anything. One example is GPT or Bloom. And we fine-tuned the foundational LLM with the prompt so it can work better on the prompt, which we call multitask prompted training. So this multitask prompted training can enable zero-shot generalization abilities in language model. And because this task, so we gather all the data and train it once, together, any kind of task at once. So because of that, like, let's say sentiment analysis is kind of similar with movie review. So it can learn each other, and a cross-task learning will happen. That's why when we train it like this, we get a better, let's say, sentiment analysis model than if we train a separate specific model just for sentiment analysis. That's a cross-task learning advantages. So what if I have a new task that it is not in the P3 list? Like, it is a lot of tasks here, but let's say we have a new task that is not there. We fine-tune the model with the new task, with your new prompt. But of course, it will be too much parameter to update. LLM is huge. We don't want to fine-tune the LLM just for one task. We can train an adapter. Or maybe if you hear prefix tuning, prompt tuning, and so on. So let's look again at the transformer layer here. There is an addition layer, which is actually just another neural network layer, but we call it adapter. So what we do when we train an adapter is we don't train everything. We don't train all the layer here. We just train the adapter layer here, and we keep everything freeze. And the amount of parameter in adapter is usually just less than 1% of the total parameter in the network, in the model. So that's why the training can be easier, can be faster. We have the same LLM. We train adapter A for task A. We train adapter B for task B. And it's the same LLM. So A and B can be different tasks, different NLP tasks, different language, whatever you need. And of course, there is a website that gather all the pre-trained adapter models. It's adapterhub.ml. you can check. And so for the NLP part, the conclusion, if you want to do X task with Y number of data, if X is in the list of P3 tasks, remember the cloud, you use the prompt pattern that is specified by P3. Else, if you don't have the data, if X is not on the P3 task and you don't have the data, you try by modifying the prompt. If you have like 1 to 10, it's a rule of thumb, doesn't need to be exact. You do a GPT style few shots, you give example, answer, something like that. There is no backpropagation. And then let's say like 100 to 10K, you can do prompt tuning, prefix tuning, adapter tuning. And then for 50K plus, you can do classical fine tuning. This is just a rule of thumb, but we think like if it is more than 50K, it's worth it to do fine tuning then. So yeah, I think you've been waiting for me to talk about ChatGPT, but I keep talking NLP. So let's see how LLM is used for chatbot. From a foundational model, let's say you download a GPT model, and then how can it be a chatbot like ChatGPT? There are at least several steps that we can think about. It doesn't need to be in this order, but for this presentation, I order it like this. This is a foundation model that predicts the next word. And then we do a task that is called completion to dialogue. And then this is a supervised fine-tuning. And then next is we put some RL, reinforcement learning. And finally, we introduce API to the model. So let's see if we put a prompt like explain step by step how to make a fruit juice. A foundation model will just continue the sentence without sugar, suitable for diet, low calorie. It won't answer the question. What we want is like this. It answered the question like cut the fruit into small pieces, put the cuts into a juicer, and so on. We want the model to realize that the prompt is a question and answer it. So between the yellow and the green, we say that the language modeling objective is misaligned. And the alignment factors are, we need the language model to be helpful, which means they should help the user solve the task. And they should be honest, like not fabricate information or mislead the user, like hallucinate. And harmless, they should not cause any damage to people or the environment. So we hope that the answer should fulfill these three kind of criteria. So of course, to do it, yeah, another fine tuning. We have a foundation model. We want it to answer our prompt instead of continuing our prompt. So we give example data that is shaped like this. The one that is not highlighted will always be the same. Like below is an instruction that describes the task, blah, blah, blah. And then the instruction, the yellow, and the green part, the response, is changing. So we need 50,000 of this at least. This is what Alpaca do. We fine-tune Llama, which is a foundation model, to Alpaca with this kind of data set. But who will make this data set? Can we make it easier? What Alpaca do is they collect 175 seed data like that, and then they use the Text DaVinci 03, it's an OpenAI API, to generate 52K instruction following examples. So now we have data like in the previous slide, 50,000 of them. And we can do supervised fine-tuning for an alpaca with 7 billion parameters. So reason I call it alpacanization because there's too many models like this. There's a bloom like equivalent to GPT-3. It's last year, it has 176 billion parameters and it's 384 A100 GPUs. And in February, there is a llama. The size decreased like 65 billion. And alpaca using 7 and 13 billion, using 4 A100 GPU. And there is also another variant, which is using a low rank adaptation. So you can train it with less GPU, like RTX 4090. It's a gaming GPU. You can get it anywhere easily. So we see the trend is like reduced compute requirement, and models are getting more open. The data set is minimal, it's 50K, so it's an opportunity for us. So next, you see in the pipeline, there is RL here. What is actually RL is doing here? Because there are some aspects that is hard to explain just by examples. So we cannot get a perfect chatbot just by doing completion to dialogue. We have 50,000 examples. We need to get more examples, but we can do it other way. First, let's see at the hands generated by Stable Diffusion. It's so weird, right? Why the shape like that, right? This is two people shaking hands, and the second picture is hand holding a chopstick. Why it's so hard for generative AI to just learn from example? Cannot just make a proper hand, because model don't know how hand actually works. Model just see that hand is like this, doing a lot of things, but don't actually know that this is connected to this. So it's hard also for us to explain to the model, no, the finger must be 5, it must be like this. Like, how can we verbally tell the model? What we can do is we give a feedback. It's a good or bad. This is good, this is bad, this is better than this, thing like that. And how does it relate it with NLP, by the way? So let's say that our chatbot can generate everything, anything. And some generated texts are improper in terms of bias, unethical, toxic, dangerous. It can generate anything. And we want it to be safe. Simply telling the chatbot to be, hey, you do not be toxic, is not enough. How you define do not be toxic? We give feedback instead. Let's say that the chatbot, like we ask, explain why the color of the sky is blue. It generates 4 kinds of answer. And then we ask annotator, a crowd worker, for example, to rank the answer from the best to the worst. And we train a reward model, like a model that automates the ranking, basically. And we use the reward model to improve the instruction-aware LLM, the chatbot that we have, using a method that is called proximal policy optimization. And this is your alpaca. You put it here. So that's how we further improve the safety of the model. And we see at the last step, there is an API. So at this stage, our model is can answer your question and maybe safe enough after some RL jugglery, and then the model is still missing these things. Let's say you want the model to see up-to-date information. You want the model still hallucinates. If you talk with foreign language, the model doesn't work. If you put some numbers, maybe you try in ChatGPT, like if you put some calculation, the model sometimes wrong. Maybe not now. and the model is also unaware in the progression of time. So we introduce tool to the model. The evolution of humans has been marked by the distinctive use and creation of tools. That's why it's significant for the model to learn how to use tools. So tools in the form of API. The model should keep its generality, like not making a specific model just for tool, and decides for itself when and how to use the tool. And it should be trained with less human annotation. Like we should not tell it very specific when to use and when not to use. This is an example of tool former from their paper. So the generation is like normal language model, like tokens by tokens. The New England Journal of Medicine is a registered trademark of, and then finally it generates this token, QA. When the model generates this token, it will actually call an API. So this kind of token special API called token, can be a question answering to avoid hallucination, can be a calculator, can be a machine translation to handle foreign language, can be Wikipedia search to add more information or extract context, and it can be a calendar. So let's see at the bird's eye view of the current LLM technologies. Actually, this is not everything. This is just what been mentioned on this conversation, in this presentation. We have a pre-trained model, which is a foundation model. For NLP, you can do multitask fine-tuning, the P3 cloud thingy. It's training with multiple NLP tasks to enable cross-task learning. You can do adapter fine-tuning. It's a small additional module for efficient fine-tuning in transformers. You can go to the chatbot route. You do completion to dialogue, which is turning completion into dialogue reply, dialogue context management. And then you can do RL, human in the loop reinforcement learning, to make the model safe, increase helpfulness, interpretability, and reduce hallucination, bias, and toxic output. And finally, you can introduce API, introducing external knowledge like real-time info, fact check, action like checkout, booking, etc. It can become a task-oriented dialogue system. And maybe after this, we go home, we check Twitter, and new things will be released. Like, so what's next? Let's discuss. Like, I think this is interesting. First is, I think, multimodality, because human communication is multimodal, and we want to integrate like speech and visual modality to the language model. Let's say you can ability to converse, to talk with your LLM using smart speaker. It will be nice. And also there is an argument like comments from people that towards universal human-machine interface, because LLM can code, maybe in the future single-purpose app will see less demand, because you can ask the model to do everything for you and there. And another thing is upweighting on low resource language. We see that this model is mainly focusing on major languages like English. So it's only good for the world's top 10 to 20 languages. And porting an NLP system to a lesser resource language, it requires a technique that go far beyond just the basic retraining of models, especially because the data is so small. Another one is to unveil the black box characteristic of LLM, because we don't know what's happening inside, and sometimes the model is also not open source, so we cannot validate it. So to build open source and well-documented models and a more rigorous test on LLM, so we can know how it performs from various perspectives. And this is released like 2 days ago. It's towards generative agents as a member of social group. So there is like a village, like a game in a village. They call it Smallville. Every people on this village is a chatbot, an agent, a language model. And then they do their daily chore, like The Sims. They go to the school, they go working, they cook, they sleep, that kind of thing. And then they put a task for one agent. You make a Valentine party, and then it plans the Valentine party. A tell B, B tell C, and then C meet A, and then say, hey, I heard you start a Valentine party, something like that. So it successfully reflects believable human behavior. So maybe in the future, we will see generative agents as a member of social group. So that's all from me. Thank you very much for your attention.
Hi, thank you so much, Johanas. Thank you, Max, today. So I'm just going to open this to the floor. I think we are able to take a couple of questions. So if you do have a question, do raise your hand and we'll walk over. So I'm also waiting for the people online on Zoom, if you do have any questions, do let us know, then we will answer. But I do have a lady over here. So, yeah.
Hi, thank you for the presentation. It was very, and I have a question. So far you talk about the NLP in general terms. So how does the NLP, how do you guys enhance your business model? Like enhance customer service or profits, and how do you guys, can you give example, like some user cases? Thank you.
I hope it works. Yeah. So we probably don't want to talk in details of what's happening, right? Especially inside Rakuten. But well, let's put it this way. I think this technology is very disruptive in many ways, right? It proves itself to be useful for a lot of use cases for copywriters and so on and so forth, right? So, well, people are using it for many things, and I think it's important to understand how the things work and adapt it to whatever business idea you have. Well, it's a little bit of hand waving, but well, that's the answer I have.
Hi, thank you so much, Max. Anyone? Oh, I think the gentleman.
Thank you. I want to know. I got one general. The first one, how do we, in the current state or in the future, could potentially solve the privacy issues when dealing with models, especially when it's like personal, conversational, or computational information, the language model. The second gen. Yeah. So. What do you think defines a human?
What defines a human?
Yeah, because being more powerful and
So for the first question, like how to privacy, how to keep privacy is anonymization is usually part of the corpus pre-processing. Let's say like a simple thing, like we want to remove all FIN number, all NRIC number. We just put a regex if you see this number remove, something like that. It's usually anonymization is just part of any textual corpus pre-processing. And I might miss other methods that is available. So that's one that
I think it's really active research area as well. So new things coming up. But indeed, you mentioned the security and privacy issue is going to be a big deal because, well, especially if you're going to use clients' data, right, to train such kind of models, you got to be really careful what you put into it. And all the models, all the language models, are very prone to capturing this very rare tokens, right? Very rare tokens such as NRIC numbers or whatever you might think of, right? So that's indeed a big issue. So you had the second question, what defines a human being? I think it's a very philosophical question in this sense. Well, there is something called Turing test, right? So basically imitation game, right? You want to imitate how human behaves. And it's quite often that it's used kind of an approximation of what on what task we can fool a human, whether it was a machine that translated the text, whether it was a machine that wrote an article, and so on and so forth. That can be one very naive, I think, at this moment, test for what human imitation of human being. But I'm sure there's also the success in large language models cause a lot of debates in what actually conscious is and so on and so forth.
Awesome, thank you. Any other questions?
Thanks for the wonderful talk. Yeah, my question is like for NLP, one problem is like having like proper label data. Do you see like these generative AI models being used as evaluators for other AI models? So something like second order AI.
Yeah, there is. We know there is a knowledge distillation also, where a big model like a teacher model actually improves a student model, where the student model is significantly smaller. And another thing is a model that acts as a discriminator for the generator model, something like that. And I think it maybe in the near future there will be like LLM versus LLM. It's also possible.
Well, I think also can probably add a little bit. Oh, it's interesting. What was interesting to play, for example, with ChatGPT, and ask the questions like, "Well, translate this sentence." Well, translate this sentence with a lower quality, and it actually can understand what the lower quality is, right? I'm sure someone can look into it and figure out how to adapt it to evaluate things for any different specific tasks as well.
Thank you.
There's recently a self-reflection also. So the answer, you ask a model, you get the answer, and then you ask again the model, is this a good answer? So that can be used also.
Hi, sorry, this is an admin question. Actually, could we get a copy of the slides that were presented today, because they were very useful?
I do not think that we will be able to share the slide, but what will happen after this is we do share the content in a video form on our YouTube as well. So we will be sharing it with Ivan and his team. Then that's when you guys can actually hop on to view this again. All right, thank you. Oh, I do have one more, just a moment. Can we take another question?
Sure.
Thank you.
Great.
Oh, can you get some of the references?
Yeah, sorry.
Right. Yeah.
Teachers,
Right. Well,
like a
oh, I think it will be shared as a part of the material, right, on the YouTube or something, right? That would require a little bit of reverse engineering, but it's a possibility, right?
look at the, what is this called? Watch it. Or look at transcripts that will be kind of not so. Yeah.
And I'll put it up for you. Thank you. Just wanna,
Okay, just a few closing notes. We have two more upcoming events. One is at GovTech towards the end of the month. So I can't remember what's the date, but you will see it when we announce our meetup. And another one with SAP next month. So there's two, and we have events lined up all throughout the year. So mostly they are going to be on LLMs. Then yeah, I think after this event, you guys can go around, but please at the space by 9 p.m. latest. I think our friends here need to go home, right? So so if you want to make up after that, I think you just do so at the level 1 lobby, or just let them close up the place to be there. So yeah, feel free to mingle, and can we give a round of applause to our speakers and hosts? Thanks.
Also, give a round of applause to yourself, because you've been a lovely audience.